was asked about the Deacon process. Deacon process, which I didn't know much about either, is another one of those applications of chemical principles to an equilibrium. So before going to the Deacon process, I thought, because it's going to tie in with Le Chatelier's principle, LCP, thought I'd go through Le Chatelier's principle, basic, very quick run through, and then to sort of apply that to the Deacon process with a little bit of history thrown in, because we like that sort of thing. Chemistry always has a context. So, Le Chatelier's principle, first of all, it is basically the principle of, one, you have to have an equilibrium, and two, whatever you do to a system that's already in equilibrium, it doesn't apply necessarily to things that are not in equilibrium, but when it's in equilibrium, you do something to it at equilibrium, you disturb it, is another way to word it. The system adjusts, and it always adjusts to undo the change that you have applied. It's kind of I often in the lesson, it's kind of like a principle taken out of chemistry, where you give a bag of sweets to a child in a classroom, and that child will get rid of the sweets one way or another. They'll stick them in their own mouth, or they'll give them to friends, or they'll take a moment and stick them in a tin somewhere. I sometimes use the suitcase and bag of money thing as well, where people save it, people invest it, people buy things with it. It's the same idea. You do something and everything gets undone. So in terms of applying it to chemistry, if we do it to a non-specific equilibrium, there are four basic things you can do. So you can remove a product. So when the process is making a particular chemical, that's the chemical that you are trying to manufacture, because it's always applied to industrial processes. That product is the one you want. You keep removing it, and the system adjusts because you keep removing one of the components of the equilibrium. Another thing, kind of the other end of that discussion, is you keep pushing in a reactant. Most of the applications of this are completely gaseous reactions, so therefore you keep pumping in a gas that is on the reactant side. Because it's often applied to gas equilibria, you mess about with the pressure, you adjust the pressure, and the other obvious thing is you adjust the temperature. Now, Le Chatelier's principle, and some people doubt whether it's exactly a perfect thing to discuss, but it's in A-level courses, so it's worth understanding that you do something, the system undoes it. So we do it in a non-specific one. So if we had there's an equilibrium that's not any particular chemical. Deliberately, there are more things on one side than the other, and as I said, everything's a gas, so let's just say, let's have everything a gas for this thing, because then we can straightforwardly apply those four things. So if you take that, the other piece of information we need is we do need a delta H value. So let's say it's minus 50, so it's an endothermic change. That would apply coming this way, therefore going that way is plus 50. So it's minus 50 forward, plus 50 back. So that'll be that. So what would happen if you keep removing C? Remove C, it just keeps making more C to replace what you keep taking out. Le Chatelier's principle. Keep pushing in B, for instance. It'll keep removing B, which makes over the right hand side with more C and D. So you keep putting B in and it keeps doing that. Obviously you do need to keep supplying A up to keep it going as well. More often the questions are to do with pressure or to do with temperature. So if you do an adjustment to the pressure, so what it means really is you set it up as an equilibrium and then you alter the pressure. You put it in a container and perhaps you squeeze, it's in a syringe and you squeeze the syringe tight, or you turn a pump on. So the pressure goes up, it will move, so we take the pressure up, it'll go to the side that reduces that pressure. Pressure is caused by the number of particles, so if you reduce the number of particles the pressure will go back down again. That means this side is favoured over that side. Goes to the right. If you take the pressure down, it does the opposite. It needs to replace the number of particles to up the pressure. No, that's not right. Replace is the wrong word. But you need to increase the number of particles in order to get the pressure back up. So if you reduce the pressure, it will go the other way, go that way to get more particles, because there's 3 on the left and just 2 on the right. Temperature wise, take the temperature up. The system will want to reduce the temperature. So if you take the temperature up, it will reduce the temperature using a reaction that takes energy into the chemicals. That's endothermic. Endothermic is the plus 50. So if you take the temperature up, this system will move to the left, as it will use the endothermic change to reduce the temperature. If you take the temperature down, it favours the exothermic reaction, putting the temperature back up again. So therefore, those are the 4 obvious things. In fact, these are the 2 that almost all questions are asked about. So you need to be able to go, here's the applied change, it's going to be come out of that list there. Obviously these 2, it's either up or down, and apply it to the system that you're given. Now I'm going to take a little pause here whilst we set up for the Deacon process, because the Deacon process is one of the things somebody asked about. So I'm just going to set the board up for that, and I'll see you after the edit. So, the Deacon process. Deacon process, sort of 1874, is a response to an Act of Parliament in the UK where for pretty much about 100 years the Leblanc process had been used to make alkali being quite important as a chemical. But one of the consequences of the Leblanc process was lots and lots of HCl as a waste material, and at the time of horrifically, I think, in the terms of what we think of today, they were just dumping it in rivers. They were dissolving water, just tip it in the river. Rivers were just, pH must have been 1, 2, not a single thing alive in rivers near industrial plants. And there was an Act of Parliament called the Alkali Act that meant you couldn't do that, and they needed a solution to just not just sitting it around and just leaving it, I suppose. And Deacon, the chemist named Deacon, I don't know his first name, I'm tempted to say John, but that's because I'm a bass player. Think about it. Never mind. So it's now called the Deacon process. Deacon process involved a reaction of the HCl gas that was the waste material from the Leblanc process, oxygen, originally atmospheric oxygen, and then using purer oxygen because costs of making that came down. And these are the 2 products, water and chlorine gas. Chlorine gas was then used and sold on. It was sold directly for the paper making process, as to make bleach for the paper making process. And it was also turned into what's called bleaching powder, which is a substance that does exactly what it says on the label, I guess. So it used the HCl waste product and oxygen, but it was an equilibrium. It's exothermic reaction in the forward direction, so therefore endothermic at plus 202 in the reverse direction. And, well, because it's an equilibrium, Le Chatelier's principle can be applied to the discussion. So when you look at that, what you really are trying to do, because quite frankly this is where the cash is, so you take a waste material, turn it into something that people want. It's a process that makes people money. So Le Chatelier, so unwanted intrusion there. Now, profit wise, more chlorine per hour, that's the point. You use Le Chatelier's principle, you can use it to predict the conditions and use it to explain what the conditions were. So you can, we'll predict what the conditions would be, first of all. So exothermic reaction in the forward direction, so that minus 202, exothermic, that means you would run it at a low temperature for maximum product amounts. But there's an issue with that, but we'll come to that in just a moment. Pressure wise, 5, 4 of them and a single oxygen, so that makes 5. 2 and 2 is 4. So if you increase the pressure, it will drive it over to the right hand side. So these are the predicted best conditions for you to have: low temperature and high pressure. You will get the same sort of question perhaps attached to the Haber process. Another one is the contact process for making sulfur trioxide. But the same idea applies. You look at the thermodynamic data and you look at the number of particles left and right, and you can use that to justify the choice. However, there are consequences to a low temperature. Low temperature slows down everything. It's rate of reaction rather than equilibrium. Slows everything down, and that kind of doesn't allow you to maximise the profit. So what happens is you get a compromise. And when you look at the Deacon process is not run at a low temperature. Initially, in terms of what the Deacon process was, they ran it at somewhere in that area of temperature to speed the whole thing up. And it was done with an elevated temperature because otherwise you think you don't make enough chlorine to make it worthwhile. Pressure wise, not massively high pressure, I call it moderate pressure. And there's a reason why you don't go to really, really high pressures. If you went to really high pressures, it would push it right over towards get loads of chlorine. But the equipment just keeps breaking as all the seals just pop open that you try to keep shut to maintain the pressure. So you don't want to go too high a pressure, because that will just be too expensive. And ultimately, all chemical processes in the real world are about maximising your profit. So when equilibrium is involved, you have to offset the amount of money you get selling the product against the amount of cost it costs to manufacture it, and run the equipment, maintain the equipment. Now, one of the things that perhaps is not clear in the textbook that this came from, which is the Salters textbook, is the saying, it talks about the I've forgotten the name of it just a second. I tried to remember it. The Sumitoto process. The Sumitoto process, or Sumitoto modification of the Deacon process, is given a mention, but I think possibly that's one of the things that people weren't sure about. So what happened is, the original Deacon process, 1874, was done with I think it was a copper chloride catalyst. So really the modifications to it, which come under a number of there's a Kel-Chlor version, there's a Shell Chlor, there's an MT, and I don't remember what the MT stands for. MT Chlor, and then there's the one that is in the textbook. No, Sumitomo. Sumitomo. All they are just, the original catalyst was copper chloride. They're just a change in catalyst. So these are just different catalysts. This one here, that uses one catalyst, and you go through. This one here uses assorted copper catalysts of varying types. This one here uses catalyst based around chromium, and the Sumitomo, oh I keep going Sumitomo catalyst, which is much more successful. Now one of the reasons these things needed modifying is when they brought in different modifications, these catalysts aren't very resilient to the reaction conditions. So it's quite acidic with all that floating around. Chlorine in itself is quite a potent chemical for reacting with things. So the catalyst would degrade. One of the things that Sumitomo has done is it's produced a more resilient catalyst, and that resilient catalyst is what's called ruthenium 4-oxide or ruthenium dioxide, and it's carried on a titanium dioxide matrix, which is an inert matrix. And so that's the catalyst there, and that's the padding. And this is a more resilient catalyst than these ones to the reagent conditions and the reactants and all the things going on. So really all that is about is just modifying the process to make it more effective, more efficient, cheaper to run. Longer lasting catalyst allows you to reduce all the catalytic regeneration costs, and that's it. Apply the same idea, like I said, to contact process, harbour process, and so it's Le Chatelier's principle. Deacon process is a particular reaction born of a particular set of legal circumstances in the mid to late 1800s. There we are. I hope that's helped. If it hasn't, I'm sure I'll get some emails telling me, no, we wanted you to do this bit of it. But otherwise, I'll see you for the next revision video. Bye bye.